Hi everyone. Um, Welcome to the second lecture of the Chapter 3 on digital modulations. In this lecture 2, we'll continue from the previous lectures 1. In lecture 1, we have introduced the fundamentals about the signal space representation of waveform. And given a set of waveform, how to construct a set of signal space and the orthogonal basis to represent the waveform. And also in previous lecture, we have discussed the three different kinds of memoryless modulations: the PAM, that modulation with amplitude, and PSK is modulation with phase, and the QAM is a quadrature amplitude modulations. And we have discussed how to find the basis and signal space for PAM, PSK, and QAM. And this lecture too, we will discuss the different kinds of modulation concepts. Is called M-array orthogonal signaling, and the example of M-array orthogonal signaling is the M-array frequency shift keying or M-array FSK. And that has that extend the modulations to m-dimensional orthogonal basis in the signal space. And then we will discuss two variations that subject to this MFSK, that is bi-orthogonal signaling and simplex signaling. For there's two variation modulation designs for MFSK, and they have pros and cons, advantage and disadvantages as compared to MFSK. Okay, so let's discuss the m-dimensional signals. That means that we have orthogonal m-dimensional bases. The common example of orthogonal multi-dimensional basis is the M-array frequency shift keying. That is the we have m different carrier frequencies. That is, as we can see, that this frequency, the carrier frequency has, we have multiple carrier frequency that m from 1 to m. In the previous three modulations like PAM, FSK, PAM, and PSK and QAM, those are single carrier frequencies, right? Single carrier frequency modulation. There's only one carrier frequency FC. But now if we have multiple carrier frequencies, then we can modulate the carrier, right? The carrier is this cosine 2 pi FC t, and this frequency shift keying is the modulation is to modulate the carrier with different carrier frequencies. So the different carrier frequency would carry different messages, right? So we have m different frequencies in the carrier, and that each carrier frequency would then represent log to m bits. Okay, so in each transmission symbol, time of capital T, that one of the carrier frequency is applied to represent the message. So here, the orthogonal basis can be obtained. We can construct the orthogonal basis for this set of signal waveforms, right? We have m waveforms, and then we can find the basis and hence the signal space for this set of m different signal waveforms by normalize each signal as mt. Capital E is the energy of each signal. So by normalizing each waveform, we can obtain the basis. This is because in here every signal waveform has to be orthogonal, so that by doing the normalization that we could have the orthogonal basis, so that has the unitary energy. So to satisfy the orthogonal condition, right? It's not any the different waveforms. To construct this type of modulation, we need this m set of bases to be orthogonal to each other. That means that the inner product, the inner product of the bases, if for different bases, the inner product has to be 0. And for the same basis, the inner product would be 1. That is the criterion, orthogonal criterion, such that we can construct the basis of the signal space. So let's do the inner product of any two bases, phi mt and phi nt, and have the inner product, right? Phi mt is this cosine 2 pi fc plus mt, and phi nt is cosine 2 pi fc plus fnt, right? And so so to have this integral to be 0, the carrier frequency fm and fn has to be designed carefully, right? It's not any in here. The carrier frequency fm is the under design, right? Under design. So by doing this finite integral, the cosine, the product of two cosine, cosine A cosine B equal to cosine A plus B plus and cosine A minus B, right? The basic formula. So and these two integral are finite integral on cosine function and finite integral on cosine function. So by calculus we can easily find the result of this cosine integral. The first term, is a sine function from 0 to t. So this is the first term, and the second term become this sine 2 pi fm minus fnt. Okay, now we need to design this carrier frequency. We can select fm and fn carefully so that this inner product can be 0. Okay, this has to be 0. The sum has to be 0 so that the orthogonal condition can be satisfied. Okay, that means so that we have condition 1 and condition 2. The easy intuitively the solution is to have the argument of this sine function to be multiple of pi. Then this sine function is 0, and also in the second term, this argument 2 pi fm minus fnt is multiple of pi. Then this sine function would be 0. Then this orthogonal condition would be satisfied automatically. Of course, you can argue that or we can have these two terms, the sum of these two terms to be 0, one positive and one negative to be then, and together the summation is 0. It's fine. Okay, it's fine, and that also satisfied. You can select this carrier frequency very carefully so that they cancel out. The first term and second term cancel out each other. Okay, as long so the solution is not unique. Okay, but in terms of system design, we just want to find the solution. Okay, the viable solution, feasible solution that could satisfy the criterion. So we choose to find fm, the carrier frequency fm and fn, such that the first term is 0 and the second term is 0. That is very straightforward. Okay, so that gives us the following two terms. That the argument, okay, the argument in the sine function has to be multiple integer of pi. Okay, so the sufficient condition, okay, sufficient solution for the orthogonal criterion would be these two we could have these two sufficient solution. The first is for the first term, okay, for the first term to be multiple of pi, and the second term would be the difference of carrier frequency fm and fm would be multiple of 1 over 2t, so that the second term is 0. Okay, so as long as these two criterion are satisfied, then the inner product of the first term and second term would become 0, and the orthogonal condition can be satisfied. And so the first term defines the summation, okay, of any two carrier frequencies in the MFSK, and the second term defines the difference of any two carrier frequencies. right? Any two carrier frequency to be multiple of 1 over 2t. For example, okay, for example, they in 4 carrier frequency m equal to 4 mfsk. Okay, then we in the time domain we can see the time domain carrier that has 4 different carrier frequency. In the frequency domain, for each interval of capital T, okay, every interval of the symbol time, right? Every interval of symbol time, right? And so that would become a sinc function centered at the carrier frequency, right? A sinc function is defined by the symbol time period, right? Symbol time period, and the frequency domain, the Fourier transform of this carrier would be a sinc function, okay, and located at the carrier frequency, this f1, f2, f3, and f4, right? Four different carrier frequencies, and each carrier frequency, right, is mfsk. So each carrier frequency would represent log 2m bits. Okay, m equal to 4, then every carrier frequency will represent 2 bits. So in the frequency domain, right, that's for every carrier frequency, but in the frequency domain is a superposition of all the carrier frequency, right? We have 4 different carrier frequency. In every time symbol, only one of the carrier frequency would show up to carry the message. Okay, and as we said, they to satisfy the orthogonal criterion, the carrier frequency has to be selected carefully. It's not any arbitrary frequency FM can be selected. Okay, can be selected for the carrier frequency. Okay, and by these two criterion, now we can see that the separation, okay, separation, that is delta F, okay, the separation of any two carrier frequency has to be multiple of 1 over 2t. So the minimum separation between the neighbor carrier frequencies that makes the minimum separation will be 1 over 2t. Okay, what is t? Let me ask you, what is t? T is the symbol time, right? T is the symbol time, right? It's the symbol time for each transmission symbol. T is the symbol time, and the separation, okay, the separation of carrier frequency would be actually determined by the symbol rate. The symbol rate would determine the minimum separation. Okay, minimum separation of the carrier frequencies, so that the orthogonal criterion can be satisfied. As we can see, with increasing the symbol rate, when we need to send transmission at a faster, higher symbol rate, what does that mean? To have a higher symbol rate that represent larger separation, right? For a higher symbol rate, okay, higher symbol rate that represent a higher frequency separation, and the higher frequency separation, and together that means what? That means that in total it requires larger bandwidth at the cost of larger bandwidth, so that to have faster, higher transmission rate, a higher bandwidth, a larger bandwidth, okay, a larger bandwidth will be required. And for M array, FSK, so then we would need M times of the minimum separation, right? M times of separation, right? So the bandwidth would be also linear to the number of transmission symbols, different symbols, right? It will be the total bandwidth will be equal to M times delta F minimum. Okay, so once we find the orthogonal basis, okay, once we find the orthogonal basis, then we can find the projection of each waveform, onto each basis. Every waveform SMT, M from 1 to capital M, there is a projection value onto the basis phi n, and the projection value is the inner product, is represented by the coefficient Smn. Okay, so given the orthogonal basis, then we can use this set of bases to design that defines the transmitter and receiver hardware architectures. Okay, so here we have the transmitter architectures. The transmitter, the objective of the transmitter is to synthesize the transmitting waveform SMT, right? We have M different waveforms for transmission. So the purpose of the transmitter is to generate the waveform that we plan to transmit. Okay, and there are M different types of waveform that is for transmission. So the transmitter design, the transmitter architecture, the hardware architecture, right, is to responsible to synthesize the transmission waveform, and the transmission waveform can be synthesized, okay, put together by the combination of the projection onto each basis, right? SMT, right? SMT is the combination of all different bases, right? But however, as you can see that SMT, S1T contains value on S11 only, and S2T contains value on S22 only, right? And the rest are 0. Okay, And the receiver architecture. The receiver architecture is the also can be constructed by the set of basis function. So this is the receiver architecture. Again, the architecture of the receiver would be constructed by the given the basis function. With this m basis, we can decompose any received signal. The received signal is unknown, right? The received signal is unknown. We don't know which signal would be received. So the receiver would prepare that all the bases. Okay, this basis would be used to analyze, right? Analyze the received signal by doing the projection of the received signal onto each basis. The projection onto basis 1, projection onto basis 2, and so on. And by the analyzing the projection values on all the bases, then we can determine which signal is received, right? And so in the transmission, that is the analog function SMT, analog waveform SMT, and this SMT could be represented by the projection on each basis, and these m values that makes a vector representation, right? This is a vector representation of the SMT, and the receiver also can decompose the received signal to m different component, and this m component makes the vector. Okay, makes the vector, and by analyzing this vector, there will be m different vectors for the m different signal waveforms. Okay, so that we can determine which, by the value of the vector, we can know which waveform is received. Okay, so far we can see that the hardware architecture of this is wireless transceiver, right? Transmitter and receiver. This is a wireless transceiver. The transceiver architecture would exactly follow the fundamental concept. Okay, the fundamental theory, the fundamental concept would define what the transmitter architecture should be, and defines what the receiver architecture should be. Okay, so the theory would guide the hardware transceiver design. Okay, let's do an example. For m equal to 2, that means BFSK. That is binary frequency shift keying. There's two carrier frequencies. So it's m equal to 1 or 2, and there are two carrier frequency. F1, the first carrier frequency is FC minus delta F over 2, and the second carrier frequency is FC plus delta F over 2, and the separation is what? The separation is delta F, right? So we have two carrier frequency, right? And so m equal to 2. Okay, so then the transmission of the waveform represent how many bits? That represent 1 bit, right? Okay, it represent 1 bit. And so the signal constellation would looks like this. We have phi 1 and we have phi 2, and the first symbol, first waveform, the S1T would represent by a projection on phi 1. Okay, and so this vector is square root EB, square root EB0. This vector, this two-dimensional vector, will represent this waveform for phi 1, F1. F1 is a slower carrier frequency, and the projection on the second basis, this vector on the second basis will represent the waveform of S2T. S2T contains a higher carrier frequency. And so as soon as we see this waveform, we know the message value. And as soon as we see this another frequency, we know the message value. There's 1 bit with different value. It's a binary transmission. Okay, and together we have this binary BFSK transmission, that every symbol time of t, we have one of the carrier frequency. Okay, every symbol time t, we have one of the carrier frequency. Each frequency represents either 1 or 0 of the message. Okay, in general, we could have m different carrier frequencies, right? In general, we would have m different carrier frequencies, and therefore we have signal space of m dimensional, and each carrier frequency or each symbol would represent k bits, k equal to log 2m, and each symbol transmission waveform would be represented by a m-dimensional vector. Vector S1 for signal S1T, vector X2 represent signal S2T, and so on. We have m different symbols, right? M different symbols. Each symbol represent k bits, and then this k symbols, right? These m symbols, represent m-dimensional signal space, m-dimensional signal space, right? And each symbol is a constellation point on the basis. Each symbol is a constellation point on the basis. S1 on phi 1, S2 on phi 2, S3 on phi 3, and so on. Okay, and the distance, the distance for any two symbols, the mutual distance for any two symbols, by taking the distance of any of two vectors, right? That also gives the minimum distance. That would be square root of 2e. Square root of 2e. That gives the distance of two symbols, and also that also gives the minimum distance. Okay. Okay, so that is MFSK. We have m carrier frequencies, and that makes m orthogonal bases in the m-dimensional signal space. So in the following, we like to discuss two variations for MFSK. First is bi-orthogonal signaling, and then the simplex signaling. Let's talk about this so-called bi-orthogonal signaling first. Bi-orthogonal signaling. The motivation for the bi-orthogonal signaling is to construct m different signals. Okay, m different signals represent k bits, right? From half of the orthogonal bases in pairs. Okay, and suppose m is an even integer. The reason is the motivation is that the m array FSK is the cost for m array FSK that require m orthogonal bases. So the frequency bandwidth is linear to m. So the frequency bandwidth is high, and the complexity is high. So if we could still have these m different signals with only half of the bases, that will reduce the complexity. That will reduce the complexity of the transmitter and receiver a lot, by 50%. And on the other hand, it could also reduce the bandwidth requirement for MFSK by 50%, because the basis number of carrier frequency is reduced. Let's see what happens here. Again, we have SMT. We have M signals for transmission. Okay, M signals, and each signal represent k bits. We are asked to transmit m different signals so that every signal could represent k bits. However, if we do some change in the signal waveform that introduce the dipole amplitude in the waveform, okay, plus and minus of the dipole, then we could create m different waveforms, right? Half of the m waveforms are positive amplitude, and half of the waveform are negative amplitude, with only half of the bases or half of the number of carrier frequencies, right? For m equal to m from 1 to half of m, right? So we need only half m of different carrier frequencies, and each carrier frequency contains each carrier frequency support two symbols each carrier frequency support two waveforms, positive and negative, right? So that we could have reduced the number of carrier frequency, and the number and the basis function, okay, is again the multiple carrier frequency, but the number is reduced to half of m. Half of n reduce the number of bases. Right. So the signal space or the constellation of this bi-orthogonal signaling would become this multi-dimensional signals. In BFSK, we only have these blue points, right? The blue constellations that is has positive amplitude signaling, and the by orthogonal signaling, the negative amplitude or the mirror of each symbol is introduced. The mirror symbol is introduced for each dimension. So that in this way we can double the number of symbols, right? We can double the number of symbols, and so that we can use less number of bases, reduce the signal space, to support m symbols, right? That gives a better utilization of the space, a better, more efficient utilization of the signal space to accommodate more symbols, right? We have accommodate more symbols, right? So that the so in this way because the number of the carrier frequency is reduced, right, by to half of m. Therefore, the bandwidth, the required bandwidth for this signaling would also reduce to half of m. Half m times delta f minima, right? So the bandwidth is saved, and so that offers better spectral efficiency as compared to the classical MFSK. Okay, so and let's take a look at the mutual correlation of bi-orthogonal signals. The correlation of bi-orthogonal signals is takes three different values: -1, 0, and +1. Okay, the correlation coefficient is defined as the normalized value of the cross inner product, the inner product of different waveforms, and normalize with normalization. As we can see that the inner product, okay, of the waveform, okay, the inner product, the normalization of the inner product would take three different values. If m equal to n, if they are the same, if this is the these are the same waveforms. It's obvious the correlation is 1. If n is equal to half of m plus m, then that represent the mirror side. The mirror side of the symbol m. If n equal to half m plus m, that would be n represent the mirror side. So that the correlation coefficient would be -1. Otherwise, if n and m are different carrier frequency, then the inner product would be 0, right? The inner product would be 0. So the correlation takes 3 values, and because of this correlation coefficient, so that's why this signaling is called bi-orthogonal, right? There's binary values of the correlation coefficient. It's not always orthogonal, right? It could be it could take dipole values. That's why this is called that the name of the bi-orthogonal signals. Okay, then we can again based on this bi-orthogonal signal basis, we can construct the architecture of the receiver. The architecture of the receiver of the transmitter and receiver, okay, that would require only half of the number of bases. Okay, the bases would be only half of the carrier frequency phi 1t, phi 2t to half of the phi m over 2t. Then any received signal can be analyzed by projection onto this smaller reduced set of signal space by inner product to each basis, and then by this by analyzing the value at the output of each inner product, that would be one of the carrier frequency would contain either 1 or -1, and the rest of the carrier frequency would be 0, right? So there again is 2 times m over 2 bases. That would help us to determine m different symbols, right? So we can tell the difference of m different symbols, right? So here we can see the benefit of the bi-orthogonal signaling. Okay, so here it is clear what is the benefit of the bi-orthogonal signaling. That would be the system complexity, right? It saves by 50%. It's because we can see that reduce the number of bases. So the system complexity is greatly reduced by this bi-orthogonal signaling concepts. Okay, so the theoretical concepts would directly lead to the complexity saving of the architectures, and and it's not really orthogonal, as we said, so it's called bi-orthogonal. Okay, so let's do a summary. Okay, let's do a summary. What is the advantage in bi-orthogonal signal? Okay, first is the complexity saving, right? The transmitter architecture will be reduced by 50% of the hardware complexity because of the number of the bases is cut in half, and the receiver architecture is reduced by 50% because of the number of bases is cut in half. So the complexity saving is obvious. The second advantage is the better spectral efficiency than FSK or the MRA orthogonal signals because the number of carrier frequency is reduced by 50%, so the required bandwidth is reduced significantly. So can you think of any disadvantage of bi-orthogonal signaling? Right? There's not really free lunch by these two major advantage. So what is any disadvantage of bi-orthogonal signals? Okay, the price we have to pay for this bi-orthogonal signal is the average energy. If we calculate because of the bi-orthogonal signal, we can find that the average energy, okay, the average energy would increase from half of E to 2/3 of E. So there is an increase in the energy. Okay, the last thing we like to discuss is this simplex signaling for the MRA orthogonal signals. The simplex signaling is to translate a set of MRA orthogonal signals from the origin to the centroid of the constellation. And what is the purpose of the simplex signaling? What is that for? And let's see what does the simplex signaling does. Say this is the constellation of an MRA orthogonal signals, right? These M different symbols, and the centroid of this pyramid of these M signals is located at the average at the average of all the symbols, right? That is inside. That's inside this cubic, okay, inside this pyramid, right? Some into this pyramid, the centroid. So therefore the so-called simplex signaling are to shift these M symbols by an amount of the averaged vector. Okay, the simplex signaling is Sm prime. The vector, the symbols become Sm prime, and the Sm prime is the shift of every Sm by the same amount of the average vector, the centroid. Every symbol Sm shift by the same amount. So that become so that it become new pyramid, right, new cubic of the constellation, but a shift of the same amount. Okay, the shift of the same amount. Okay, and so you may wonder, what is that for, right? Why we are doing this simplex signaling by shift of this constellation and by a certain amount, right? And so there is, of course, there is reason for doing this. To understand the idea, the motivation behind simplex signaling, let's take a look at the characteristics of simplex signals. The first is the energy. With the simplex signaling, the new symbols, right? The new symbols of the simplex signal is the true norm of the simplex signal, right? True norm of the simplex signal that represent the energy of the new constellation. And the energy would be, by definition of the simplex signal, that is the shift, right? A shift of the original symbols. And then we can find out by do the product, then we can find out this energy of this new simplex signal, right? That would be reduced by 1 over m of Ne. So the energy is reduced, right? So the reduced energy is actually the main motivation of doing simplex signaling. The main motivation is in doing simplex motivation is to reduce the energy, right? Remember, in the bi-orthogonal signaling, the energy is increased, right? There's higher power consumption due to the increased energy for bi-orthogonal signaling. And in here, the purpose of the simplex signaling is to reduce the energy, right? You can see energy required, transmission energy of each symbol is reduced. That is the main purpose. Okay, and the second characteristics of simplex signal is the equal cross correlation. The correlation of the simplex signals, again, by definition, the correlation coefficient is the normalized inner product. Okay, the normalized inner product of the simplex signal, Sm prime and Sk prime, the normalized simplex signal. And the if for the same symbol, okay, for the same symbol, of course, the cross correlation, the correlation will be 1 for the same symbol. For different symbol, okay, for different symbol of the shift symbol, for different symbol, if m not equal to k, then the cross correlation is negative. is negative, is no longer orthogonal. We can show that the result of this cross correlation by in here. Here the cross correlation of these two simplex signal, right, is by definition is the inner product of this the shift version of the symbols, right? And doing the by doing the simple calculation operation in linear algebra, right? Then we can find out this inner product would be equal to minus 1 over m times of E. And the denominator is the amplitude of each simplex signal. As we have seen here from the reduced energy, the amplitude of each simplex signal is a square root of 1 minus 1 over m. So their amplitude are the same. The length of the vector, is the same. So the product of the lengths would be 1 minus 1 over m times E is again this value. So the ratio of the ratio that gives the cross correlation coefficient, that would give, then it gives this negative value. If you look at this cross correlation, that shows that the orthogonal property does not hold, because the cross correlation is non-zero, right? So we have non-orthogonal signals, non-orthogonal signals. So you may wonder, okay, now we have a non-orthogonal signals. Would that be a problem, or is not a problem? Okay, so let's take a look. Let's check this result. Just take a look at the example of simplex signal. Okay, the example of simplex signal. The M-array orthogonal signal, the original M-array orthogonal signal that has the m vectors, right? That is the m vectors takes the together. We have all the m signals, right? And these m signals makes this constellation. And the simplex signal of this set, okay, the simplex signal of this set of MFSK, M-array orthogonal signal, would be a shift version, of each vector or each symbol. Each symbol is shifted by the constant amount. Every symbol, every component, right, is shifted. Is shifted. So every column here represent one of the simplex signal symbol, and we have m different columns that represent all the m different simplex signals, all the different simplex signals. And again, as you can see, in here, these m signals are orthogonal to each other, and these m simplex signals are then non-orthogonal. Okay, non-orthogonal. So we need to verify. Okay, we need to verify whether this non-orthogonal result would introduce any problem. Let's check the inner product for MFSK and MFSK with simplex signaling. This is the classical MFSK. The inner product for each on each basis would be either equal to square root of e or 0, right? And only one of the bases contains value, and there are m different bases. That is the M-array FSK, and the distance, right? And the distance for any different symbols. Okay, the vector distance for any two symbols would be square root of 2e, the d minimum, square root of 2e. And so that is the M-array FSK. The distance is the square root of 2e. And if we have the simplex signaling for this MFSK signal, the inner product of the simplex signal onto each basis, that would become square root of e prime, or this negative projection, where e prime is the energy of the simplex signal. Okay, E prime is the energy of simplex signal, and then this as we said, the E prime is the reduced energy for simplex signal, is a reduced energy, and the received signal, okay, the received signal would be decomposed, analyzed by all the m bases with two different values. One of the value is of the square root of e prime, and the other rest would be this negative projection. And that, okay, so and the vector that makes the vector of this Sn prime, okay, that makes this simplex signaling symbols, right? And the and as we can see, we can verify from the figure. We can see that the distance between of any two symbol, okay, the distance will not change at all. Okay, the distance will not change at all because it's the constant shift of this constellation that makes this simplex signaling. So the relative distance between any two symbols will remain unchanged. Okay, we can verify from here as well. The distance will remain unchanged. Therefore, although the symbols of this Sm prime, this simplex signaling, it become non-orthogonal. However, the error performance will not be affected. Okay, will not change. Because the distance is not changed at all. And therefore, this simplex signaling, we can have the advantage. We have the advantage of the reduced energy. We have reduced energy, and the without the impacts on the minimum distance. Okay, and compare with M by orthogonal signaling, there's no benefit on complexity. Okay, there's no, because the number of bases remain to be M different bases, so it remains unchanged. And the detection is probably a little bit more complicated because it's non-zero value of in the calculation. So that's for simplex signaling. Okay, so again, let me summarize it. Okay, the simplex signaling that offers the reduced energy. The bi-orthogonal signaling offers what? The bi-orthogonal signaling offers a reduced spectral bandwidth and reduced complexity. Okay, at the cost of increased energy. And the simplex signaling offers reduced energy. It's power saving. But no benefit on complexity and no benefit on spectral efficiency. Okay, so it depends on the system requirement. People can choose different design strategy of signaling. So that's the test your understanding. Okay, for the lecture 1 and lecture 2. Okay, first, why modulation is needed. Okay, so far we have discussed on modulation. Why modulation is needed? It's because the modulation is trying to have the message key into the carrier waveform. The carrier is perfect sinusoidal signals, and the modulation try to key the information into the amplitude of the carrier, or the phase of the carrier, or the different frequency of the carrier, so that the carrier can carry the message. That is the purpose of modulation. Okay, and what is digital modulation versus analog modulation? The digital modulation means that we are working on digital message, discrete message, or binary message input, and modulate the binary bit stream into the carrier. That is called digital modulation. On the other hand, the analog modulation is to modulate the analog message onto the carrier. Okay, So the difference between digital modulation and analog modulation is that the message is digital. The message you try to modulate onto the carrier is digital, then it's digital modulation. It's analog message, then it's analog modulation. Okay? And so how to find a signal space that represent a modulation scheme? In the lecture 1, we have discussed how to find a signal space by finding the orthogonal basis. Then we have the signal space, right? And how to find the orthogonal basis? Standard procedure is by the Gram-Schmidt procedure. Gram-Schmidt procedure, we can find the basis and the signal space. However, as we said, these for the same signal space to cover the signals, but the bases are not unique. Okay, the bases are not unique, and so and in PSK, in PAM, we can find the single carrier basis, in cosine 2 pi ct or sine 2 pi ct to represent the signal space, the I channel and Q channel. And in the multi-dimensional signals, signal space, we can find in the multiple carrier frequencies signaling, we can find m different bases, that each basis that has the m different carrier frequencies. Okay, and again, it's the same signal space, but the basis is not unique. Okay, so far that's the for the lecture 2. Thank you.